So friends, here we are again for a video lecture series on electrical measurement and instrumentation. This is Unit 4 and in Unit 4 we will be looking here for CTs, current transformers. I am Neeraj Gupta and this is AKGEC Digital Studios where we are recording lectures on electrical measurements and instrumentation subjects. So here are the contents. Contents basically are about the CT. What is CT? Introduction to that, then their phases. Then we will be deriving the expressions for the current transformers, like ratio error and phase angle errors, derivations that we will be doing here. Now, first of all, let us see the construction of the current transformer. Current transformer basically is nothing but a kind of a transformer which is specifically working upon to measure the high currents, where high heavy line currents are to be made to be dropped into the measuring instruments range so that they can easily measure the currents which are flowing through the heavy lines. The CT has two windings similar to a transformer called primary and secondary. Primary winding has lesser number of turns while secondary has a more number of turns because it is a current reduction here. So the whole circuit current passes through the primary winding, and it is desirable that the voltage drop across primary must be as low as possible. The CT has fewer number of turns of larger cross sections, thus the voltage drop in the primary gets reduced to a great extent. So here is a specific description of this CT. So the primary turn is, generally we keep it as, in bar type CTs, we keep primary number of turns as 1, and here are large number of secondary turns. And this is connected in line with the, in series with the line where the current is to be measured. So here, as I told you, this is the line where the current is to be measured. The current which is flowing through here, and this is secondary number of turns, this is primary number of turns, and it is connected in series as well. Whatever line current we have to measure, it is connected in series with that. The secondary has more number of turns as compared to primary, not in many folds, but comparatively has larger number of turns in secondaries. So where the ampere meter is connected, or energy meter is, or watt meter, or a transducer, or a protection relay, whatever is connected in the output circuit of that is with the low resistance. In general, the output, that is secondary of a current transformer, is always capped at a smaller voltage. The CT must be connected with a low impedance meter, as I told you, to keep the magnetic flux in the core up to its rated flux capacity. The flux in the core above to the rated capacity causes saturation of the magnetic core, which leads to complete failure of transformer. If this flux goes high, then the windings will be harmed. Their varnishing would be gone, they could get burnout. These things could happen if the secondary circuit is secondary circuit impedance or load is increased. So the CT secondary must not be left open circuited when it is connected to a line. It is preferred that it should be a very low impedance, or it should be a kind of an ampere or a transducer whose impedance is very less, or it should be shorted. The flux in the core increases manifolds and it causes the CT core saturation. That's what I told you. If it is left open circuited while connected to a line or connected in line, then the damage could be done to the windings. The terminals here, P1 and P2 shows the primary winding of the CT, and terminal S1 and S2 shows the secondary winding of the CT. The ratio, CT ratio 2000 by 1 means the secondary current will be 1 ampere if the primary current is 2000 amperes. So you can see that what amount of reduction in current the CT is providing to us, and what level of current can we measure with the help of this current transformer. with the simple ampere meters or ammeters. This is the equivalent circuit of a CT, where RP and XP are primary resistance and reactance. IP is primary current, VP is primary applied voltage. These are magnetic field loss components. This is RE and the magnetic component XM. IE is the iron loss current and IM is the magnetizing current, and I naught is the resultant of this IE and IM. While primary induced voltage is EP, secondary induced voltage is ES, secondary current is IS, secondary resistance and reactances are RS and XS, RP and XP are the connected load or burden. So here we specifically develop a flux phi between those two primary and secondaries. So this is the complete equivalent circuit. Here are the description of these parameters, that what could be these parameters, and will be the turn ratio, RS, XS, all these parameters I have already told you about. IM is CT magnetizing current, I naught is CT excitation current, phi is the flux in the CT, and theta will be the phase angle of the CT, that is angle between I1, IP and IS, that is primary and secondary currents. Now let us come to the phasor diagram, which is most important here to understand. So the phasor tells us that the flux lies as a base phasor. First of all, we take flux as a base phasor, and if flux is the base phasor, the magnetizing component of the current will be in line with that. So IM will be in line with that. This is IM. The resultant of and the iron loss component, obviously it will be leading by 90 degree. So that will be leading by 90 degree. Resultant of IE and IMR is I naught. That is the excitation current, no load current that we call as in transformers in general. So the resultant of that is I naught. Now the resultant of primary current, that will be measured with the help of the counterbalancing component of the current, which is coming from the secondary side, and this I naught. The resultant of this will be given only after that. So we cannot draw IP like that only. We need to find the counterbalancing component of the current as well. So if we try out the secondary circuit, the secondary circuit will be like that. If we is simply assume the direction of this IS, that is secondary voltage, because the load is inductive in nature. Load is inductive in nature. The current will lead to voltage. So Vs is the secondary voltage, terminal voltage, and Is is the secondary current, which will be leading by a factor of delta. That is phase angle of the load. So if we draw like that, the Is in just phasor position of that, and because the expression says that I1 upon I2 equals to N2 upon N1 equals to the turn ratio N. So if we bring this Is into the primary domain, so it will be N times of Is. That is secondary, when it is repeated in or transferred to primary side, it will be N times of Is. So we have written this component as N times of Is. So this primary current resulting of this I naught, this phasor and this phasor, as we complete this, we can find out the IP value. And as I told you guys, that theta is the phase angle error, that is angle between primary current and the secondary current. That is, this is your phase of secondary current. This is secondary current, and this one is primary current. So theta will be the phase angle error between IP and Is. Delta is the angle between the resultant voltage. This will be the resultant voltage. What will be the total KVL equation in the secondary loop? That is terminal voltage Vs plus ISRS. So IS is the phasor in this direction. So parallel to that, a phasor will be there at 90 degree of that, because the inductive voltage is leading by 90 degree. So inductive voltage is here. So here the resultant of these all will be, we will be getting as ES, that is secondary induced voltage. So this is the complete phasor of the transformer basically. So this is general transformer. It happens in all the transformer. Now what about the particular phasor of expressions, where we can find out the spatial expressions for actual ratio and phase angle errors. So for that we have taken a referred phasor. Referred phasor is what? It is actually the complete phasor with respect to the primary side. When we draw a phasor with respect to the primary side itself, then from there we can find out the actual ratio. Actual ratio is defined as IP by IS. So actual ratio, to find out the actual ratio, we have considered this primary referred to primary side circuit, the phasor itself completely. So if I say the angle between I naught and this flux or IM is alpha, we have considered this as alpha. This angle IP and IS, that was delta, that is angle between primary voltage EP and this IC, that is delta. So if we consider here and we extend these lines to a point B, draw a right angle triangle like this. So this angle will be what? The angle will be 90 minus alpha minus delta. This angle will be 90 minus alpha minus delta. And we consider this triangle A, B and C. This is we considering as O, origin point. So there are two particular point lines which are component of this OB, that is OA plus AB. Similarly, here you can see, consider this IP also here. So if we talk about the transformation ratio, or we consider it as actual ratio, for finding transformation ratio, we need to calculate the primary current as per the definition and then divide it by secondary current. The other name for that is also the actual ratio, IP by IS. So now let us consider the part of phasor. IP already we are having, that need not to be calculated separately, or the value of that needs to be calculated in terms of I naught, NIA, secondary current and various IC. So that is what we are trying to evolve here. So if we consider here as, so IP can be calculated like this. If we consider IP, so IP, if this is, we are considering as, yes, I naught square plus 2 I naught NIS cos 90 minus alpha minus delta. So if we write it as, so what it becomes, cos 90 minus theta becomes sin theta. So I naught square plus NIS square 2 I naught NIS sin alpha plus delta. C2 ratio is equal to IP by IS. As I told you also, that is actual ratio. So if we write it by R, represented by R, so R will be I naught square plus NIS square plus 2 I naught NIS sin alpha plus delta divided by IS. So this will be the expression for actual ratio. Now, the assumptions that we further take into the consideration. So, as compared to primary, although it is very sufficient, but if we compare it with the primary current IP, which is of hundreds of amperes, then it is comparatively very small. Therefore, the above expression can be, the last equation can be simplified by writing it as simple n is square. I naught can be written as I naught sine theta. That is what we are doing over here. Sine theta, not theta in the sense sine alpha plus delta. So n is square plus I naught sine alpha plus delta square plus 2 I naught n is sine alpha plus delta. So this assumption we have done, and we have simply replaced this I naught by this expression I naught sine alpha plus delta, because it is very small. So if we consider this, so it becomes NIS plus I naught sine alpha plus delta whole square. So as it becomes a whole square, the square root is gone, and it becomes NIS plus I naught sine alpha plus delta upon IS. And further on simplification, the expression comes to be as N plus I naught by IS sine alpha plus delta. So from this expression, it will be clear that the transformation ratio is not equal to turn ratio. That is, N is not equal to R. N is what? This is what? Turn ratio. And this is what? Actual ratio. So this is the difference between these two gives us the error that we call it as ratio error, and it will be represented percentage ratio error as, hopefully it will be calculated in next slide. So this Kn minus R upon R into 100. Here Kn is a term that is not known to us currently. Kn is nominal ratio. Nominal ratio is what? When it will be defined as Kn will be rated primary current divided by rated secondary current. The rating with which it has been provided, the transformer has been provided. So when this R needs to be become N, what should be the possibility? If alpha goes 0 and delta goes 0. If alpha and delta will be going to 0, so what will happen? The core loss is equal to 0 and burden will become purely resistive. So this is an ideal condition. It generally don't happen in real practice or in practical scenarios. So because the loads are generally inductive or capacitive in nature, having some reactance as well. They are not completely resistive all the times, or complete resistive load is not possible actually in industrial applications. So this is a practically impossible situation. I hope that derivation or evolvement of this actual ratio is clear to everyone, and the ratio error. This is percentage ratio error if we calculate it as Kn minus R upon R, and this N is not equal to R in real time situations, because N is your turn ratio that is based on number of turns in primary and number of turns in secondary. So that does not becomes equals to this actual ratio R in practical situation, and between the error between these two will provide you the ratio error. Now the further exploration, this previous one was for simply finding out the errors in their actual ratio and turn ratio. Now the second thing that will be the phase of the both currents, that is IP and IS, will not be same. So if the phase will be different, what will happen? There will be a change of or shift of output. To find out that particular phase angle between IP and IS, we need to consider this triangle again from the figure, that is O, BC. Again, we have to explore here. Tan theta will become BC by OB. So if we write it as I naught sine 90 minus alpha plus delta upon OA, that is this one, NIS plus AB. NIS plus I naught sine alpha plus delta. So since theta will become very, very small, primary and secondary is not much. So theta will be smaller. So we can consider tan theta as theta. This is another assumption that we are considering over here. So theta becomes I naught cos alpha plus delta, because sine 90 minus alpha minus delta becomes cos alpha plus delta. And if we put the value over here, so again the same assumption, very, very less than n times IS. That is counterbalancing component of the current. Hence, it can be neglected because it is in denominator. So theta becomes this one, I naught cos alpha plus delta divided by NIS, and theta becomes again, if, opening this expression, cos alpha cos delta cos A plus B formula, cos A cos B minus sin A sin B. So opening this becomes I naught cos alpha cos delta minus I naught sin alpha sin delta upon n times IS. Now again, visualizing the phasor further, we come to know this, the projections of this I naught in horizontal direction and vertical direction. So we will be considering the value of IM and IE over here. So IM is I naught cos alpha and IE is I naught sin alpha. Putting these values in this expression to bring it into the terms of IM and IE, so it becomes theta equals to IM cos delta minus IE sin delta in radians, and for converting it into the degrees, we need to multiply it by 180 degree by pi. So this is how the phase angle between primary and secondary could be calculated also. So these two parameters, that is ratio error and the phase angle error, are very important to understand regarding the operation of a CT or any instrument transformer. That instrument transformer, why we call them instrument transformer? Because they are used to bring the unmeasurable voltages and currents. For example, in this case, the current which was unmeasurable, that is the example I gave, 2000 amperes primary line current, 2000 ampere currents. So for that to bring into a lower ranges, the transforming action and reducing the current up to a 5 ampere, 10 ampere or 20 amperes, to bring that into a ranges where we can easily measure them with the help of our normal instruments. These transformers or instrument transformers have been introduced. Similar will be the case with the PT, where 11 kV, 32 kV voltages have been measured with the help of the same situation. Here, number of primary turns were lesser, secondary number of turns were comparatively larger. But in case of a PT, primary number of, because it is a step down transformer, but that is a voltage transformer. This is a current transformer. That is why this particular ratio is just opposite to that. Now, here comes this ratio error that I have introduced into the actual ratio slide. The CT ratio error is defined as the per unit deviation in the transformation ratio from its nominal ratio. So nominal ratio was represented by Kn there, and it was defined as ratio of rated primary to rated secondary current. Transformation ratio, that is we termed as actual ratio or R, divided by again R multiplied by 100. So this is the ratio error. Or we write it out also as percentage ratio error. Since the burden of CT is generally resistive, therefore the power factor of the burden is unity and delta becomes 0. In that case, if resistive load is there, then obviously there will be, because that particular for a load, delta will be calculated as tan inverse Xc by IS. This will be the factor. If it is purely resistive, what will happen? This Xc component goes 0, so it becomes 0, delta as 0. So it remains only I naught sin alpha for a resistive burden as it defined, I naught sin alpha by Is, and the actual ratio becomes N plus I naught sin alpha is what? IE by Is. So this is R for the case of completely resistive load that we define as. Next error is the phase angle error. So phase angle error that we have already calculated and we defined. Phase angle between primary and secondary must be 180 degree. It should be 180 because for a transformer, primary and secondary must be out of phase completely 180 degree. The deviation in theoretical aspects, but that does not happen. These are not 180 degree in phase opposition. There is a deviation from that because this is theoretically possible or theoretically ideal situation that 180 degree out of phase it should be, but deviation from that is giving you a phase angle error. So the phase angle error of the primary and secondary is called the phase angle error. The phase angle between primary and secondary current of the CT is denoted by this angle theta. Since burden of CT is generally resistive again, so delta becomes 0. So that expression that we have calculated for theta, 180 by pi Im cos delta minus I sin delta upon NIS, 180 by pi Im cos delta I sin delta upon NIS. So it becomes, what happens? Delta becomes 0, cos 0 is 1, sin 0 is 0. So it remains only 1 Im by NIS. Since burden of CT is generally purely resistive, power factor of the burden is unity and hence delta becomes 0. So this is the phase angle error of transformer. Now phase angle error is due to the magnetization. The reason for that is due to the magnetization component of the current. Because of the magnetization component of the current and iron losses errors have been introduced. That is why these two are affecting the 180 degree out of phase shift. So the value of these Im and IE must be decreased for reducing the phase angle error. These could be avoided. This angle could be only avoided when Im and IC are reduced, as these will be low, or actually what it is, magnetizing loss and core component loss, core loss. So these are the references from where I have collected the information and have been representing to our students. That is AK Sahani and Internet for Pictures. The basic difference that we have talked now regarding CT and instrument transformer and a transformer is that the transformer function is to step up or step down. Obviously, that is the normal function of a transformer. But how they are different? They work on the principle of transformer itself. Instrument transformers are working on the principle of as same as that of a transformer, but due to their turn ratio and actual variations in their scenarios from theoretical transformers, these have been typically used to measure the very high voltages and currents by our normal instruments. For example, a very high current of 2000 ampere rating is brought into the ranges of 5-10 amperes, which can be simply measured with the help of this normal ammeter and normal voltmeters. So thank you very much for the session.